SwayamPrabha. Digital India. Educated India.
Hello, I welcome you all in this course on refrigeration and air conditioning. Today we will discuss on vapor compression cycles. We will start with the modified reverse Carnot cycle, vapor compression refrigeration cycle, and we will work out one example in this lecture. If we take a reverse Carnot cycle and depict on temperature entropy diagram, it is going to have two constant temperature processes and two constant entropy processes, A, B, C, D. A to B is compression, B to C is heat rejection, CD is isentropic expansion, and DA is heat addition from the surroundings, that is QL, this is TL and this is TH. For air refrigeration cycle, these processes are difficult to realize because during these processes constant temperature has to be maintained constant, the temperature has to be maintained constant, and these processes will automatically become very slow. But in case of vapor compression refrigeration system where vapors are used as a working fluid, the process D to A can be realized during boiling of vapor, and process B to C can be realized during condensation of vapor, because at the boiling and condensation of vapor the temperatures remain constant. So we can use, if we use vapor in the Carnot cycle, we can easily realize the constant temperature heat addition and constant temperature heat rejection in the process. Now the second problem with the Carnot cycle is we need an expander or expansion turbine. An expansion turbine in this case is going to be very small because refrigeration systems are of the capacity 2 ton and 4 ton normally we use for domestic applications or even for the large refrigeration systems. This work attained during process C to D is going to be very small and it may not sufficiently supplement the work consumed during process A to B. First of all, at the state C, if we redraw this Carnot cycle for the vapor, then as we know there is a saturation line on temperature entropy diagram where the entire vapor is in liquid state, and there is another saturation line where entire vapor in gaseous state, and the Carnot cycle will lie somewhere here. During process B to C, the entire vapor will be converted into the liquid and heat will be rejected, and during process D to A, heat will be taken from the surrounding and the boiling of refrigerant will take place. Now process C to D represents the isentropic expansion of the vapor, not vapor, isentropic expansion of the liquid available at C. Now as I said earlier, the provision of expander or the turbine is not advisable here because the work output is very small, and this may be the case that the work output is barely sufficient to overcome the friction losses during this process, and expanders and turbines are costly items, so it may not justify the cost of the system as well. So instead of using an expander, this process C to D is made isoenthalpic. Now if we have high pressure liquid here, it can be throttled to the low pressure with the help of a throttling device. So instead of having process C to D, we will have a process, this D will be shifted to this point. D will be shifted to this point, and the entire refrigeration process cycle will be A, B, C, D, and this is constant enthalpy process. Now we will try to find refrigerating effect and work interaction during this cycle. Now I will further expand this diagram. Just a minute. We'll use different pen. Now A, B, C, D, E, this is F, or this is F, or we will say this is E, this is F, then G, and H, I, J, I, K, L, M, N. Now why I have done this? I have done this so that suppose I want to have enthalpy at C. This line will pass from here. Suppose I want to have enthalpy at C. Immediately I will take area of this figure. The area of this figure will show the enthalpy at C, because enthalpy at this point H is 0. Sorry, the temperature at this point is 0, absolute 0. So this is a imaginary point. So this will give us the enthalpy at C. Similarly, if I want to have enthalpy at E, the area of this diagram will give us enthalpy at E. So this is the, we will try to find the COP of this cycle with most basic technique. Now starting with the refrigerating effect. Now refrigerating effect we will be getting during this process. It means the area of this area will give us a refrigerating effect, right? We can find this area we can easily find. This area is SB minus SC. This is entropy at this point minus entropy at this point multiplied by temperature. The temperature here is T2, suppose the temperature here is as T1. So T2 multiplied by entropy at point B minus entropy, because this is a right rectangle. So entropy at point B or point A, or and entropy at point F, but sorry, the point D. But we do not have the value of this entropy change during FD. We have entropy of F, we have entropy at A, but we do not have entropy at D, and we do not know the length of this line. In order to find that, we will start with the assumption that this is an isothalpic process. Since this is an isothalpic process, enthalpy at C is equal to enthalpy at D. Enthalpy at C is equal to enthalpy at D. It means the area under this, so area right here, enthalpy at C is equal to area CHLC. Enthalpy at D is equal to area DEHMD. So the enthalpy at C is equal to enthalpy at D. It means this area is equal to this area, right? If we equate these two areas, it means that some overlapping is there, because this area and this area, so this area is common to both. This area is common to both cases. It means this area is equal to this area. I repeat, enthalpy at C is equal to enthalpy at D. Enthalpy at C will be given, can be attained by taking this area. Enthalpy at D can be attained by taking this area. Out of these two areas, this area is common. So we can always say that this area is equal to this area. Now, if we are able to find the area of this diagram, we can find the area of, definitely we can find the area of this diagram as well. Now, the area of this diagram, area CEF is equal to SC minus HE, HC, this is area, minus HE, this area, minus area EFLI, EFLI, this area. So, this will provide us, this equation will provide us area for CEF. Now, area CEF, as I said earlier, is equal to SC minus HE and area EFLI, that is, sorry, EFLI. Now, in order to find this area, we can say that at state F, the entropy is same as in the case, as in the state C, and entropy at E is known to us, and we, with the help of these values, we can find the value of area EFLI as SF1 minus SF2 multiplied by T2. So, area of CEF is equal to HC minus HE minus SF1 minus SF2 multiplied by T2. Now, as we know that this area is equal to this area. So, area of FDML is this much. This is equal to area of FDML. So, the length of FD or entropy change while going from F to D is going to be equal to area CEF divided by T2, and this will give us the value of FD. Value of AF is already with us. The value of AS is, so here AF, we can find the value of AF. This is going to be the change in entropy during this process, or entropy of gas at 1 minus entropy of liquid or fluid at 1. Since we have the value of AF, we have the value of FD also. Now, the refrigeration effect takes place during process DA. So, the length of the DA is going to be AF minus FD. So, through this process we can find the value of DA. Now, for the refrigerating effect, if we multiply DA by T2, this will give us a refrigerating effect during the process. Regarding the work by the compressor, for the work by the compressor, the area of this diagram will give the work of the compressor. This diagram constitutes this rectangle, and this area we have already calculated. This area we have already calculated. So, this is the area CEFC, area CEFC, which we have already calculated, plus this area, and this area is going to be equal to SG1 minus SF1 multiplied by T1 minus T2, or the area of this rectangle. In order to have clear insight of this phenomena or this process, let us work out one example. An example is given here. in a R744 based refrigeration system. R744 stands for carbon dioxide based refrigeration system. The cycle operates in the temperature range of 20 degree and 0 degree centigrade, and their corresponding latent heats are 175 and 235 kilojoules per kg, and difference is liquid energy, that is liquid enthalpy at 20 degree centigrade and liquid enthalpy at 0 degree centigrade, and the difference is 35 kilojoules per kg. Find COP of the system if vapor is dry and saturated after the compression. So again we will plot temperature entropy diagram. And this is temperature T1 and T1 and temperature T2, constant enthalpy process. Instead of constant entropy process, we have constant enthalpy process. So this is 1, 2, 3, 4, and then it will come 5, 6, 7, 8, 9, 10. I will give the direction of the process 1 to 2, 2 to 3, and 3 to 4, and 4 to 1. So here we have to find the refrigerating effect and the work done by the compressor, and T1 is equal to 293 Kelvin and T2 is equal to 273 Kelvin, because this is at 20 degree centigrade, this is at 0 degree centigrade. And we do not have any information about the entropies. We do not have information about the entropy at 3 or entropy at 5. We have the value 35 kilojoules per kg. Q 5 to 3 is equal to Cp T3 minus T5 is equal to 35. Now T3 minus T5 is 20, so Cp into 20 is equal to 3.5. So Cp is equal to 1.75 kilojoules per kg Kelvin. Now we will note this value here. Cp is equal to 1.75 kilojoules per kg Kelvin. Once we have the value of Cp, we can find the change in entropy during this process. Now change in entropy during this process means delta S 5 to 3 is going to be Cp natural log T3 by T5. Now we have Cp, value of Cp with us, it is 1.75 natural log 293 divided by 273, because T3 is equal to T1 and T5 is equal to T2, and this gives us the value of 0.1237 kilojoules per kg Kelvin. We will note down this value also. Delta S53 is equal to 0.1237 kilojoules per kg Kelvin. Now after this, area of 3563, area of 3563 is H3 minus H5 minus S6 minus S5 multiplied by T2. Now H3 minus H5 is already with us, it is 35 kilojoules per kg. S6 minus S5 we have already, S6 is nothing but S3, so S3 and S5 we already know, it is S6 minus S5 is 0.1237 multiplied by 273, and this will give the value as 1.23 kilojoules per kg. Now I am repeating here, we have calculated the change in entropy between 3 and 5. So, if we are coming from 3 to 5, the change in entropy is 3 to 5, the change in entropy is 0.1237, and this change in entropy we are using here as S6 minus S5, because X is equal to S3 multiplied by T2 and H3 minus H5, H3 minus, so this expression will give the area of this. Now this area, as we know, it is an isenthalpic process, so H3 is equal to H4, so this area is equal to this area. This area is equal to this area, we have already done that, and this area means it is, so area 3563 is equal to area 6894 is equal to T2 multiplied by distance, let us say 64 is X, multiplied by X. Now X is equal to 1.23 divided by 273, and that is going to be equal to 4.5 into 10 to power minus 3 kilojoules per kg Kelvin. Now after attaining the value of X, now we have the value of X. Now this one S1 minus S6. Now change in entropy during process, this condensation. We have latent heats. So latent heat at 20 degrees centigrade. So S 2 to 3, when coming from 2 to 3, it is going, sorry, latent heat, let us say entropy during process 3 to 2, that is increase in entropy. So process 3 to 2, that is increase in entropy, is going to be 175 divided by 293, and 175 by 293 will give us the value of 0.5973 kilojoules per kg Kelvin. Now we have the change in entropy between 1 and 6, and we have the value of X. Now if we subtract the value of X, we will be getting the entropy change during process 4 to 1, and that is 0.5973 minus 4.5 into 10 to power minus 3, and that will give us, and this change in entropy multiplied by T2, we will at the same time we will multiply it by T2 also. So if it is multiplied by 273, that will give us the value 161.8 kilojoules per kg. That is the amount of refrigerating effect we are getting here. Now work consumed by the compressor. Work consumed by the compressor is 0 area of this rectangle plus this value of this area. So this area we have already calculated as 53, we had already calculated as 0.1237 kilojoules per kg. So the work will be 0.5973, that is change in entropy between these two, multiplied by T1 minus T2, that is 293 minus 273. That will give the area of this diagram. So area of this diagram is S2 minus S3. S2 minus S3 we have already calculated, that is 0.5973 multiplied by change in temperature plus area of this diagram, that is 1.23, we have already done. Now this expression will give us the value of work consumed by the compressor as 13.18 kilojoules per kg, this is small k, kilojoules per kg. Now we have both the values, refrigerating effect and work consumed by the compressor. So COP of the system is going to be 161.8 divided by 13.18, and that is going to be equal to 12.3. Now today I have explained you how to find COP of a vapor compression refrigeration system with the basic principles, and on the same concept I have solved one numerical example.